Okay, good afternoon. Welcome to the next Ground Source Heat Pump Association webinar. We're going to give it just 5 minutes to allow everybody to join. So starting at 1:05 with the proper presentation. But while you're waiting and having a cup of tea or whatever you're doing at the moment, just to let you know about the next few webinars, which are up on your screen at the moment. So we're planning to run these every week, and there's going to be a whole raft of topics all about all kinds of heat pumps and financing them and operating them and designing them. Next week we've got Dave Jones from Haveld Renewables talking about smart grid ready heat pumps, which should be really good. That's at 1 o'clock next Thursday. And then after that, we've got a series of seminars on borehole systems, and that's designing them, finishing them, drilling them, all sorts of things. So if you're really interested in boreholes and that side of the heat pumps, then do tune into those. They will all be uploaded onto the GSHPA website. So if you can't make them, you can go and watch them afterwards on there. And then we've also now got a YouTube channel, so you can go and watch them on there if you would like to do that as well. So we've got webinars booked now until mid-August. So every week we'll update you with what's coming up. And just to say that if anybody's got any particular burning topics that they would like covered, if you send them into the GSHPA, we can look to include them, see if we've got somebody who can talk about that. So yeah, feel free to ask questions. We're here to try and teach as many people as we can about heat pumps of all types, and get them out into the market and get this industry moving the way that we want it to go. So we'll just give it another couple of minutes. Chris Davidson has kindly offered to moderate the group, so if you have questions while I'm talking, please feel free to put them on the chat, and at the end of the presentation, which is probably going to be about 20-25 minutes, we can have a look at those questions, and Chris is going to help me out with sorting those out and making sure that they get answered as best as we can. Okay, I think we'll get started. There's quite a few participants, so we will get started. So today's presentation is all about the value or importance of high quality engineering design, and it's specifically about heat pumps, but it can also apply to other types of heating plant or cooling plant. So some of the things I'm going to talk about are across the board, not just heat pump specific. So just a tiny bit about my background and why this is so important to me. My background is in manufacturing engineering. I'm a mechanical engineer by trade, and when I was working for some of the manufacturing companies, Rolls-Royce and Bombardier, and there's obviously loads of others of them, design is extremely important, and it's a huge part of the process of getting a product from in somebody's head out onto into a jet engine or a power station or something like that. They've got very strong design principles, and there's loads of design tools that people use. So you may be familiar with some of them, like Six Sigma, process design, lean design and manufacturing, change control, requirements management, design review. You basically spend quite a lot of time at these companies doing training on how to design and how to design in a specific way. So the building services industry is not so strong, and I'm not going to say that design doesn't happen, because it absolutely does, but it's definitely not as strong as it is in the mechanical engineering manufacturing industry. So since I've been doing this sort of job, working on heat pumps, I have gone out to a lot of sites where design has not been considered early on, and there's all kinds of problems that have occurred because of that. So really it's all about how do we avoid the problems that people get from lack of design or lack of thought early on. So in the building service industry, what we come up a lot with is things are based on rules of thumb, based on experience. I hear, well, we've always done it this way. I hear that a lot. And there's nothing wrong with rules of thumb and basing things on experience. And sometimes that can actually be the best thing to do, but without having a specific design process, even if it's just a quick, a proper drawing and a handover with the client, that still needs to be done, and there's still a lot to be said, and a lot of problems can be avoided by not just relying on rules of thumb, but by doing some proper design. So and the reason for that is clients, I come across a lot of clients who don't want to spend a lot of money on design, or they don't want to spend any money at all on design. They just want to go straight in there and get the heat pumps in. But when things go wrong, they magically seem to get hold of a lot of money to put things right. And the simple fact is that you can spend a relatively small amount of money up front on design work for these kind of projects, and it will save you a whole heap, even thousands or millions of pounds later on, when you find that your project hasn't worked as you expected, or it's failing, and you then have to go back and replace things, or you have to redo things, or you've got miserable clients which can kill your business. And actually a lot of what I'm going to talk to you about is the importance of money, which is the bottom line of everything, unfortunately. I'm just going to stop on the design side for a second and just talk very quickly about heat pumps themselves. And I know there's quite a few people out there who are not necessarily techie, and I've been asked, quite a few times, well, I don't actually know how a heat pump works, and why is it so special to think about design when you're designing a heat pump project? And I thought this little diagram might be quite useful, because this explains why it's important to think about how you're going to design in a heat pump and how you're going to operate it before you get started with installation. So the heat pump is essentially a box, it's generally a box, and on the left-hand side you've got primary energy, and this is your free energy that comes from the air or the ground or from the sea or the river or mine water or sewage. There's all sorts of sources that we can use to run a heat pump, and it's free energy. So we want to maximize free energy. Inside the heat pump, you've got a refrigerant circuit, which has got either refrigerant as a gas or a liquid. I'm not going to go into that cycle. If you've got questions, please send them through, and a lot of us can talk to you about that. That's probably a webinar in itself, to be honest. But inside the heat pump, you have a compressor. And the compressor works on electricity, and electricity is definitely not free. Electricity is quite expensive. And if you were on Bean's webinar last week, you'll have heard all about, our electricity prices in the UK. So we want to minimise how much electricity goes into the heat pump and maximise the primary energy that's free. So the compressor is essentially squeezing the refrigerant. So the amount of squeezing it has to do, a bit like when you pump up a bike tyre, you have to put in a lot of energy to pump up your tyre so that it's really hard. That takes a lot more energy, and if you translate that into a compressor here, if you were trying to make your heat pump work very hard, you need a lot more electricity, so it's going to cost you a lot more money. And the way that we describe the way a heat pump works, or how efficiently it's working, is with the coefficient of performance, the COP. And very basically, that is how much electricity do you need to make the heat that you need versus how much free energy you're getting from the source. And what you're trying to do, as I say, is to maximize free energy and minimize electricity going to your compressor. So in an air source heat pump, a badly performing heat pump may take air at -5 degrees in the middle of winter. And if you're then trying to make it produce 70 degrees C water into your building, whether that's your house or a leisure centre or a factory, your COP is going to be really low because you need a lot of electricity to boost that temperature from -5 up to 70. So that's a bad example. A good example is where you have higher temperatures coming in on the primary side. So that might be mine water at 20 degrees, it might be a sewer at 12 degrees, it might be brine coming in from the ground loop at 8 degrees, and you might only want to deliver 40 degrees C on the building side. So that's your useful heat. And that might have a very high COP, and that's really where you want to be. And in the course of a year, that COP will change because you can't change the primary energy temperature, but you can have a big effect on the building temperature you want to achieve. So that's why we really need to be thinking about how we're going to introduce heat pumps into buildings. The last thing to say there is that standard heat pumps generally don't generate heat above 60 to 65 degrees. You can get heat pumps that will do 90 degrees C plus. They tend to be bigger and working on refrigerants like propane and ammonia. But if you just want a sort of normal, cheaper, off-the-shelf heat pump, you need to be looking at making sure that your heat pump's working at about 60 degrees C max. And that's where either your design engineer or your supplier will be able to help you think about that. So back to design. What can go wrong if a design is not exactly right? So client perspective, when I talk to lots of clients, some of them are mine and some of them have come to me because they've got problems. The first big one is they've had a heat pump installed, or they've heard a bad story from a neighbour or a colleague. Heat pumps don't work, full stop. And the trouble with that is that it does massive damage to our industry, because we know that those of us who are in the know that heat pumps do work, and they can work in the majority of situations. But if things haven't been designed or thought about properly, the chances are you will have a situation like this where your client is saying heat pumps don't work. I don't want another heat pump. I hate them. They cost too much, which is the next point there. They cost too much to run. So the reason they cost too much to run is because the compressor is having to work so hard and it is absorbing so much electricity that your electricity bill shoots through the roof, which is not right. Comment also, heat pumps only work in new buildings. That's probably, again, a story that they've heard from somebody that says, oh, we put it into our old building and it didn't work. Reasons being, building is cold now. It didn't used to be cold, but now we're cold, or we don't have enough hot water for showers and baths and things. We have another seminar in a few weeks talking about retrofitting heat pumps in old buildings, so I'm not going to go into them now. Suffice to say that heat pumps do work really well in old buildings, and we have lots and lots of examples of where that's happened. And if you're investing in a heat pump, you may also have this problem. You didn't get the RHI you were expecting, the renewable heat incentive payments, or I didn't get the project payback I was expecting. And that's generally because either the heat pump isn't working, it's too big, or it's too small, so it's not working as much as you thought it was going to, or the COP is very low, so you're again taking a lot of electricity, which is costing a fortune, back to cost again. So these are sort of things that can go wrong, and I and others will regularly hear from people who have got heat pumps and that haven't quite gone to plan. And here is a big list, which I am not going to go through in detail. Other things that can go wrong that are not necessarily from a client perspective, but things that can happen if something is just not being done right from the start. And this is where design comes in right at the start. So huge electricity bills we've talked about. Freezing the ground, and I'm going to just show a case study of that, about what can happen if the borehole or horizontal loop serving your ground source heat pump hasn't been designed correctly. Heat emitters is a big one. So heat emitters, if they've been connected to a gas boiler doing 80 degrees C, and suddenly you stick a heat pump on doing 40 degrees C, is the heat emitter still going to do what it should be doing? And sometimes it will, and sometimes it won't, and that's all got to be considered at the start of a project, especially if you have a big building like a factory or a school or a university. That can be a real issue that needs to be considered early on. Legionella needs to be considered. So if you're going to be storing hot water, you need to think about Legionella prevention. If your heat pump has been put in too big or too small, that can have an issue, which again affects your project paybacks. And then the things below there can affect actually any plant. So things like minimum flow rates. If you don't get the right flow rate, your heat pump will switch itself off. System integration is really, really important if you're going to be doing a retrofit heat pump, so putting in a heat pump where you may have an oil boiler or a gas boiler already. Thinking about how your heat pump is going to integrate hydraulically and electrically and with the controls is so important. Don't just think you can stick a heat pump in and everything will be fine. It may be, that's an accident. So make sure that you talk to somebody and get that thought about and designed properly to start with. Couple of ones I've come across, and I have got a couple of case studies. Heat pumps don't fit in the plant room. Talking about this to Chris just before we came online. Our maintenance is difficult or impossible because the heat pumps haven't been designed into the space properly, so you can't access the pipework at the back, or pumps are up in the air, or you can't even get into the plant room to even look at anything. So thinking about that. And then drawings and documents, you know, going into a job after it's been done, if there's anything that needs to be adjusted afterwards and there's no drawings or documents, you're really on a back foot working out what needs to be done. So just got 3 case studies. So the first one here is something I did last year. It's a guy who owns a lot of houses in a rural area, and he decided to do the right thing by his tenants who were all on oil boilers or electric heating, and he wanted to put in ground source heat pumps at all of his houses to save his tenants money and also to save carbon emissions. So a double whammy there, which should have been really good. Unfortunately, after a few months or maybe even a couple of years, the tenants, although they were on oil previously, were saying that their electricity bills had gone up by up to 50%. And actually what they should have seen is their electricity bill being less than their oil bill. So tenants were very, very unhappy. They were out of pocket because their electricity bills were high. And in some cases, they were also cold because the heat emitters hadn't been upgraded. And that's the worst thing, actually, that you have an unhappy tenant or a tenant who can't actually afford to heat their house after having a heat pump put in. That's just unacceptable, really. The picture I've got there was just one of the houses I went to where they had a heat pump installed in a shed outside the back of the house. The shed looked like it had come from Argos, bargain basement Argos. Already water was getting in, the heat pump was corroding. The brine pipe that you can see on the side here was actually propped up with a piece of wood, so it wasn't even properly supported. There was so many things here, I can't go into all of them, but this is the sort of thing that should have been considered before they started work. There was no metering on any of the heat pumps, so we couldn't interrogate to find out whether the heat pumps were underperforming, or getting to the bottom of why this was happening. No consideration given to electricity tariffs. So if you run your heat pump at night, you can take advantage of lower electricity tariffs, and you can use thermal storage to offset the running cost of your heat pump. As it was, the heat pump was just running almost uncontrolled all the time, and there was very little consideration given to tenant controls, so understanding how to control the heat pump. The guy who owns these houses is now going to have to spend another load of money to go back and put in metering and to correct plants in every single house, and I think he had about 12 houses to go back and amend. So it's ended up with very unhappy tenants, and the guy who owns it, who wanted to do the right thing, now having to go back and spend an awful lot of money to get this fixed. All of these things could actually have been avoided with just maybe a couple of days of design upfront. Case study number 2, I talked about freezing the ground earlier. This is a church centre, so a new build church centre in Yorkshire, and they had a little heat pump installed to do their parish centre. The heat pump over time stopped working. In fact, I think they only had it in about 2 or 3 years, and it just stopped working. And their driveway between the church and the vicarage suddenly acquired speed bumps because the ground was freezing year on year and causing the tarmac in the drive to lift to the point where they couldn't drive up the drive anymore because the car wouldn't go over the lumps. And it turned out that originally they'd had 5 30-metre boreholes put in because the driller said they couldn't drill deeper than 30 metres because the rock was too hard. That is not true. And they capped off 2 boreholes because they were leaking, so we're left with 90 metres of borehole, and the heat pump just couldn't cope with 90 metres of borehole, so the ground froze. So this guy, the vicar of the church, contacted us and said, could you do some investigations? And we wrote him a spec for a new heat pump, and this one needed 200, so it's the same size of heat pump, and actually they needed 240 metres of boreholes, 3 new 80-metre boreholes. So it's another drill rig site, another set of boreholes being drilled, and a new heat pump. So more expense for the client, but the only upside to this was that he could now get commercial RHI, which he hadn't been able to before because the heat pump just wasn't working, and he didn't have any documentation to do the RHI application. And then the last one, this was more to do with accessibility. It was a 360 kilowatt ground source in a leisure centre in the north of Scotland, supplementing their oil boilers. But the plant room was so small that although you could walk into the plant room, you couldn't get around. There was pipework everywhere. The borehole pipework, or the brine pipework, was leaking and it wasn't being routed anywhere, so it was just pouring out all over the floor. The heat pumps were switched off. They were getting a COP of less than 2, and also the pressurization unit was undersized, so the pressurization unit here, so the expansion vessels were undersized, so the system was just failing on a high pressure fault constantly, and they couldn't get RHI. So I don't think actually in the end they just scrapped the system and they just went back onto oil, which is a real shame. So they'd spent a lot of money. 360 kilowatts of ground source with boreholes is expensive, and if they're not going to do anything with it, that's a bit of it's a massive white elephant of a project. But what I've put in here is that it's relatively straightforward to design an energy centre. So this is just a 3D model of an energy centre building, very simple. Heat pumps inside and a thermal store, some expansion vessels, some pumps, and you can do, this is a good example actually, because you can see that if the thermal store was inside the building, you'd be poking out the roof. This sort of thing can be done really quickly, and it enables you to make sure that whatever you've got on site will actually fit in the space that you've got, and if it doesn't fit, you need to stop, or you need to think about doing something else like an energy centre outside rather than using plant room. And it's very quick and easy to modify the design. So once you've got that set up, you can put more heat pumps in or less heat pumps. You can play around with the layout of everything. And it also helps obviously when you go to planning. If you do need to go to planning, you've got your drawings and models. So again, could have been resolved, could have been, none of this could have happened if a bit of design had been applied at the start of the project. So finally, just to sum up, lots of bad news stories. I have to say, I see loads and loads of really good installations. But in order to avoid being one of those people who complains and says my heat pump doesn't work, or my electricity bills are too high, or I can't even get into my plant room, what do you need to do? So I'd say, first of all, early on in your project, employ a qualified engineer or somebody that knows what they're doing to design the system. And the analogy I use is that if you were designing a big building like a factory or a new school, you wouldn't expect your builder to rock up and just start building. You would expect to have an architect on site first who would do all drawings, and then the builder would build to the drawings. So it's exactly the same for a largish heat pump system project, especially in retrofit. It's so important to get somebody involved early on if you're looking at retrofit. There's no sort of cut-off for what sort of size of heat pump constitutes large, but it is up to you. If you're just doing an air source heat pump in your 2-bed semi-detached house, you probably don't need a qualified engineer on the job. But if you were doing a 50 kilowatt heat pump at a care home, you might want to get somebody involved. There's trade bodies out there such as the Ground Source Heat Pump Association, there's the British Drilling Association, the Heat Pump Federation, which has been launched. Use those trade bodies to find good quality people to advise you. And although lots of installers do design, and I'm not knocking that at all, don't expect your installer to design a system. So they won't, although they can do things that I certainly can't do, which is to be on site and do the installation and commissioning and all that. I don't do that. They wouldn't necessarily do all the drawing work beforehand and make sure that some of the things I've talked about have been done properly. If in doubt, request drawings and specs before you start. At least you've got something to go back to if something isn't quite as you expected. And you can always request an independent reviewer on the large jobs. So if you do have a drawing you're not quite sure, then you can get some independent advice, even if it's just half a day or an hour, just for someone to look over it and say, yes, it's definitely worth it, because as we've seen later on, it can cost you thousands of pounds to rectify something that's gone wrong. So you might as well spend an hour or a day or however long it takes beforehand if we start. And it's a cliche, but it's true. If you fail to plan, you can plan to fail. Things will most likely go wrong if you haven't planned these bigger systems in. So thank you for listening. I hope that's been useful. If you have questions that haven't been answered today because we've run out of time, you can forward them to info@gshp.org.uk and we'll pick them up there. And you can also visit our website to see if there's anything interesting or anything that answers your questions there. So thank you. And I'm just going to see whether Chris has got any questions for me.
Yeah, we've got a couple of questions come in, Laura. We've got one from Glucan. Apologies if I've mispronounced that. Could you recommend a software for heat pump site feasibility studies?
The software, right, okay. Well, because each project is so different, there isn't really a one size fits all, because you might be looking at heat loss to size your heat pump, in which case you could be using something like IES, but that's quite a big package of software. It's quite expensive. So you could do something like that. There isn't, some of the heat pump manufacturers have online tools which are very useful. So you can have a look at sizing a heat pump and how many you'd need, but that's specific to the heat pump manufacturer. I mean, to be honest, I work a lot of spreadsheets. You can build your own models quite quickly. So looking at finances, RHI income, heat loss analysis and things like that, and sizing heat pumps that way. I hate to say it, but there isn't a software that will do your full feasibility. There's software that will do bits and pieces, but you really are better off talking to somebody, even if it's just, as I say, a 10-minute conversation, just to give you a bit of a steer in the right direction.
We have if you have a look on the Ground Source Heat Pump Association website, there's a number of consultant members who will be more than happy to do feasibility studies. Most of them will have a quick look at a project free of charge as well, and then propose a more broad package of work. So hopefully that helps.
Yeah.
I've got a second question from Peter. 65, you mentioned a 65 degrees C maximum temperature output for certain types of heat pump. Is that irrespective of the input temperature? And I just, I mentioned back to Peter that generally the highest temperature a heat pump will be able to achieve is set by the pressure and refrigerant circuit. So whilst an improvement in source temperature will help efficiency, it generally won't increase the output temperature. Do you agree with that, Laura?
Yeah, I think, yeah, I mean, I obviously had to keep things very basic in the presentation, but yes, your output temperature will be very much dictated by the refrigerant you're using, as Chris has just said, and also by the source temperature. So most of the heat pump manufacturers will publish tables where you can see what the incoming temperature is and how that impacts not only the capacity of the heat pump, because the capacity changes as well, so the kilowatt output changes, but also your maximum flow temperature that you can achieve on the building side.
Thanks, Laura. Questions just come in from, I can't read your name unfortunately, Craig. With propane, etc., can we expect higher flow temperatures as the technology progresses?
Yeah, yes. So there's a couple of manufacturers, I won't name drop in this, but there is a couple of manufacturers who are over in Sweden and Finland who are doing propane heat pumps. So and also isobutane. So they will achieve up to, I think it's 85 degrees C, and you can do that right now. And you can do it with a variety of incoming temperatures, and they do air source and ground source. The issues will be your COP. So your COP will, although it will be better than you'd expect if it was like a standard refrigerant heat pump, it's still not extremely high. And also they are expensive. I will say that they are expensive. So if you have a reason for using a high flow temperature heat pump, then yeah, absolutely go ahead and use a propane heat pump. Think about the ATEX rating, the explosive rating, but that can be overcome. But always my first recommendation is try and get your temperature down first to get your COP up. But yeah, definitely propane heat pumps are available now that will do 85 degrees.
I think the key point I would bring out what Laura said there, Craig, is that it's incredibly important not just to rush for the highest temperature. You really need a reason to need to go to higher temperatures, and hopefully it can generally be overcome. A second question from Craig: will the higher temperature heat pumps be RHI eligible?
Yes. So lots of people are concerned about the SPF, minimum SPF for RHI. So for RHI purposes, you need a minimum COP of 2.9 and you need a minimum SPF, which is seasonal performance factor of 2.5. If you look into, I mean, I've done loads and loads of RHI applications, unfortunately. You often ask for the COP at a given flow temperature. So they ask for it at brine 0, water 35 or water 45. They don't ask you to give the COP at design temperatures. Not in my experience of 160 RHI applications. Even when I've tried to explain that we're running the heat pump at a higher temperature, they don't want to know. They're not that interested. They just want to know what it is at British standard temperatures. So therefore your high temperature heat pump is probably operating at a COP of greater than 2.9 at these design temperatures, not your design temperatures. If you don't achieve the SPF over the course of 20 years, because you have to upload your heat meter and electric meter readings every quarter, even if you don't hit an SPF of 2.5, they can't withdraw your RHI. That's in the regulations. So it really is a recommendation rather than an absolute. So you could run your heat pump at 0 degrees brine and 80 degrees C flow temperature for 20 years and you will still be able to get RHI, but your electricity bills might be phenomenal.
Thanks, Laura. Peter's asked the second question: is the space take for air source and ground source heat pumps similar? I expect you mean space requirements.
Okay, so the heat pump themselves look fairly similar. So the ground source heat pump is an internal box. The ones they're all very different, but you might be looking at something like the size of the fridge freezer for, say, a 60 kilowatt ground source heat pump. But obviously you've got to think about your boreholes and horizontal loops, which will take up an awful lot of space. Oh, sorry, if it's horizontal, it'll take up an awful lot of space. But you don't see that because you reinstate the ground. So that's then under the ground, you can build on top of that. If it's an air source heat pump, they have to sit outside, but they are more or less similar kind of size. They will sit outside unless you're going for a much bigger air source heat pump, which might be maybe a 600 kilowatt air source, and in that case you'd have an indoor unit and you'd have an outdoor unit. The outdoor unit is the evaporator, and so for big air source you need a lot more room because you can't bury the evaporator unless you stick it on the roof, but you can bury your boreholes obviously. I hope that answers the question.
Excellent, thanks, Laura. Another question from Richard, which may be better addressed actually in a future session, but I'll certainly put it to you anyway. If cost and space is not an issue, would you recommend horizontal loops or a boreholes?
Yeah, if space is not an issue, horizontal loop is probably going to be cheaper for you, especially if you have your own diggers. So if you're a farmer or you've got a property development, you can take your own digger out and dig your own trenches, so you're saving money there. And providing the horizontal loop has been designed properly, you shouldn't have any issues with efficiencies. Boreholes, obviously, you're going down into a much more stable temperature further down in the ground, and you need a lot less boreholes. So if you're space constrained, definitely boreholes are the way to go. If you're not, horizontal loop will be cheaper. There may be a tiny reduction in efficiency, but that will probably be offset by the cost saving of going horizontal. Do you agree, Chris?
Yeah, absolutely. There is quite a difference in the physics of horizontal systems and boreholes. So, for example, boreholes are practically unaffected by weather, whereas horizontal systems, you do see seasonal fluctuations. So there are some physics differences. Both technologies are equally good, and it's horses for courses, in my view, depending on space available, what plants available, as Laura says. Another question from Peter. Can there be a significant difference between building, modelling, heat, stroke, cool requirements and subsequent operational use experience, and can this be addressed in design in any way? So can we under or overestimate the requirements up front and deal with it down the line, I guess is the summary of that.
Okay, so yeah, I mean, cooling demand tends to be much higher in peak than heating demand. So if you're looking at a heat pump that might do both, simultaneous heating and cooling, you might end up oversizing your heat pump to enable it to do the peak cooling demand. What I usually suggest to people on big projects is that they have multiple heat pumps. So if you think that your initial peak demand, your peak heat demand is 600 kilowatts, you might end up with 3 200 kilowatt machines. And it means that if you have over-egged a 600 kilowatt and you actually only need, say, 450 kilowatts, it's affected you capex wise, but performance will still be fine because your smaller heat pumps will be able to modulate and achieve that lower heat demand. If you and also the other benefit from doing that is that you will stay in the RHI tier 1 longer. It's not the reason to do it, but that is a sort of side benefit. As long as you have more than one heat pump and it's not just one big heat pump that's trying to modulate down to a lot lower demand, you should be fine.
Thanks, Laura. That was great. There aren't any other questions, so just one last call. If anybody else would like a question answered, then please pop it in the chat now. Okay, so one coming from George. Is it right to say that the wetter the soil, the better the conductivity?
It's probably one for you, Chris.
Yes, it is right to say, but you've got to make sure that the soil is going to remain wet. It's not seasonally wet, for example. So there's quite a lot to that in terms of assessing how conductive the soil is going to be, particularly at the surface. As you get into boreholes, it's much more consistent, so it can actually be easier to take full benefit of wet ground conditions. Another question from Peter. Are there practical limits to the size of air source heat pumps? I'm thinking here of megawatt sized units. Where there is insufficient ground available.
Yeah, I think that's going to be the limiting factor. I saw a presentation earlier this week about, I think it was something like a 3 megawatt air source heat pump system that's been installed in the desert in somewhere, not in the UK. The evaporators for big air source can become quite big. So you've got to make sure that you can fit. So the first thing you'd need to do is to work out how much land you've got available. Have a chat to either someone like me or a supplier and say, right, how many evaporator beds can I fit on here? You can buy vertical ones, you can buy horizontal ones. The vertical might help because they're just thinking about that though. Vertical ones have to have a certain space in between them so they don't affect the airflow between them. So yeah, the answer to that, long way around, yes. The limitation is the space that you've got available for big air source. Okay,
excellent. So there's a second follow-up question coming from George on the soil. Can I just double check if the groundwater is a good conductor of heat? Will the ground source heat pump have better efficiency in the wet soil? Okay, George, do you want me to take that, Laura?
Yeah, yes, please.
There's quite a lot in what you asked that question. It's actually a very clever question. You generally set the limits of the water temperature in the ground loop as the boundary for your design. And so whether you've got a high conductivity ground condition or a low conductivity ground condition means that you need more or less pipe rather than affecting the efficiency of your system. You can, if you got exceptionally good conductivity, decide, or any conductivity for that matter, decide to put in more pipe, which will mean more moderate ground loop temperatures and better efficiency. And there are industry standards around what those temperatures should be. So that's a very clever question, George, and hopefully that answers it. It's probably an hour's conversation, though, I'm afraid. Okay, any final questions? Okay.
Okay. Thank you very much. If you do have questions after this, do feel free to drop us a line and we will get back to you. Yeah, but hopefully that has been helpful and given you some food for thought.
And just to say thank you very much, Laura, for the session, and we look forward to seeing you all again next week.
Yep. Okay, bye then.
Thank you. Bye.